Hello friends, we have spent quite some time on discussing the different events that are associated with the process of comminution. So we saw that the entire process of comminution is generally categorized into crushing and grinding. So you have crushing events and you have a grinding event. Now, even though these are the primary events or these are the primary techniques that constitute the overall comminution process, there is also rather an integral technique called as screening. The primary distinction is these process or these techniques, they reduce the size of your feed, whereas the screening helps us in categorizing or ensuring that the right amount of feed is fed into the appropriate technique. So the appropriate feed or the right feed is allowed to pass through the or allowed to enter into the grinding mill, and this is ensured by screening. The screening in the overall process of the comminution occupies a section wherein a closed circuit is involved. So if you could recollect the overall process chain that is associated with the comminution process can be categorized into one wherein you have open circuit and the other wherein you have a closed circuit, and screening plays an integral role in the closed circuit. Now, having seen that, so we have seen what crushing is, what grinding is, and what is the role of the screening. So crushing, it involves several stages, so therefore that constitutes an open circuit of the overall comminution chain, and often grinding is comprised of just one step, and in order to ensure the right transition occurs between the tertiary crushing and the grinding, the screening is involved. So these are the three integral techniques or three integral aspects of the overall comminution process. So having seen this, so we have these two and screening involved. Having seen these schemes of events that constitute the comminution process, now we need to move on to the other process or the other technique that is usually involved in the overall mineral processing, that is concentration. So during the general introduction of the mineral processing, we saw that the overall mineral processing events that are involved can be categorized into comminution and concentration. Comminution helps in fragmenting the particles, thereby reducing its size and ensuring that we have a mixture that comprises of mineral particles, gangue particles, and some of the locked-in particles. And the concentration, what it does is it helps us separate the mineral particles from that of the gangue particles. It helps us separate our valuable particles from that of the impurities. Now, before getting into, so you have comminution and the next step is concentration. Before getting into this concentration, of course, the basic theory behind the concentration will be significantly different from that of the comminution. So before getting into the concentration, particularly in concentration, we will be talking about the individual techniques that are involved. Before getting into that aspects of concentration, we will try to consider a process that acts as a buffer between comminution and concentration, that acts as a process that helps us relate the transition from comminution to concentration. Now, during the comminution, we have screening event that in itself is quite different from the fundamental fragmentation process. So comminution, it has fundamental fragmentation processes that are crushing and grinding. In addition to that, we have screening that is quite different but also an integral part of comminution. Now, before moving from the comminution to concentration, there is also a similar integral process that is involved, which has some aspect that is more close to that of concentration. So if you define comminution as the processes that involve fragmentation and concentration that involves the process of separation, that is separating the particles that are rich in minerals from the separating the particles that are rich in impurities. If you define the concentration in that way, there is a process, there is an event that is placed between comminution and concentration that is more close to the concentration than the comminution. So this process acts as a buffer. This process acts as an intermediate step between comminution and concentration. So if you look at the scheme of things, in the comminution, there are events that primarily involve or that primarily does the fragmentation process, and in that you have something that is separating. So in that comminution itself, you have an integral process which the role of the process is not to fragment but rather to separate. So whenever we talk about separating, separation is an event that is associated with concentration. So even in the framework of comminution, you have a process which has some resemblance to the concentration. The concentration does nothing but separate the mineral rich particles from that of the impurity or gang rich particles. Now in screening, we also do certain separation. The separation aspect remains the same. In screening, we do separation, but here it is based on the size. So essentially, the fundamental operation that is happening in screening and concentration is separation. However, that is based on size. Now, we'll be considering, in this lecture, we'll be considering a process that is again more than screening is close to. So the only similarity between screening and concentration is the process of separation. However, in case of the process that we will be considering, that process will have even more closeness to that of the concentration, and this process is referred to as the classification. Now you can refer to classification, or you can think about classification as screening on steroids. So meaning it is a more advanced version of screening. So classification is rather, you could refer to it as a more advanced version of or more sophisticated form of screening. So again, what classification does is it also separates the particles based on their sizes. And the way it separates is quite different from that of the screening, because classification is employed only to these particles which cannot be handled using conventional screening techniques. So essentially, the screening is placed between tertiary crushing and the grinding process. So therefore, the screening, the particles that are fed into the screen, that are placed onto the surface of the screen, they have a specific size range. Now after the grinding process, the output you get from the grinding process is much more smaller, and those cannot be directly placed on the surface of the screen. So that cannot be easily handled using the industrial screening setup. So for that, you need to take a different approach, and that approach is referred to as the classification. So what classification does is, it performs an action similar to that of the screening. It separates particles based on their sizes, and the reason we need to include classification is because the classification is used when the particle sizes are much smaller and they cannot be handled by the industrial screening equipments. Now such particles are usually found as an output of grinding. Now the output of grinding is fed into these classifiers, or the output of grinding, it is exposed to this process of classification, or it is fed into the equipment, the corresponding equipment classifiers, or in terms of the process, it is exposed to the process of classification. The smaller particles are then sent for further processing, that is concentration, and the particles that are greater in size, the particles that are not experiencing sufficient grinding, they are sent back to further grinding. So one place where classification is used is to ensure that the sufficiently small particles are alone sent to the subsequent concentration processes, and the particles which have not achieved the required sizes are sent back to grinding. Now we need to ensure that, or we need to be absolutely clear that the output of the grinding is significantly smaller than the output of the ternary crushing or tertiary crushing. So therefore, even though the tertiary crushing or the screening can be directly employed for the tertiary crushing, for this the combination cycle, that screening can be employed, the classification is required when you want to handle the output of grinding. So that is one of the primary difference between classification and screening. That is, classification handles the particles that cannot be handled using conventional screening processes. Now one other difference of when you consider how the classification is the operation of the classification, one other difference when compared to screening is that the classification is able to categorize more than one form of minerals, meaning it is able to categorize, say for instance, we are able to separate or classify a given mixture into more than two. So in case of screening, you just have two sections or two forms of particles. One is undersized particles, and the other is oversized particles. So these are the two outputs that you get from the screening event. However, in case of classification, it is possible to have it is possible for us to classify more than two forms of poly. It is possible for us to categorize or have as an end product more than two categories of the mixtures. So in case of screening, it's just undersized or oversized. In case of classification, it is possible for us to have more than two categories of the end products, more than two categories of the fragments. So these are two initial differences between the screening and classification. One is the size that is handled by the classification process, and secondly, the output that you get. Screening gives you undersized and oversized particles. Classification, much more or many more forms of particles, many more categories of particles can be achieved. Now, when you consider the operation, we have extensively seen the operation of the screening process, how the screening process works, how the screening process is achieved in the industrial scale. In case of classification, this process is quite different. The way the materials are classified, the particles are classified during classification depends on the velocity with which the particles travel. So essentially, the particles are allowed to travel, and depending on the velocity with which these particles travel, the different particles are then categorized. So we need to then have a medium, or we need to have a setup in which these particles are allowed to travel. Supposing you can easily think about a cylindrical hollow barrel, and you can allow or you can feed in particles of different sizes, and you can see how these particles are free falling, and depending on the velocity with which they are free falling, we will be able to distinguish them and we will be able to separate them. So this is the generalized version or the simplistic description of what occurs during classification. However, if you think about this generalized description, wherein you are considering an empty barrel, a cylindrical barrel, and you are allowing the particles to fall through, and depending on the velocity in which they are falling, we are allowing or we are categorizing the different particles. So this is, if you consider this general description of the classification, if you say this is how classification works, there is a bit of inaccuracy associated with this description, because imagine you have a barrel that is present in a vacuum, and you allow the particles of different sizes to fall through it. So we have particles of different sizes, and we allow these particles to fall through this barrel, and essentially this barrel is placed in a vacuum. Now when you allow these particles of significantly different sizes, noticeably different sizes, so you also have particles of this size, and you allow these particles to fall through this barrel which is placed in a vacuum, a cylindrical barrel. Now essentially you can imagine, or you can think, if you could, if I don't know if you have come across this sort of thought experiment, but there is also an experiment that is being performed. Essentially what happens is, if you consider a vacuum, and if you consider particles of different sizes and allowed to fall, what would happen is, irrespective of the size, irrespective of the weight, irrespective of the other factors of the individual particles, all these particles travel at a similar speed. And there won't be any differences in which, or in the velocity in which these particles are flowing, these particles are falling down. So essentially, these differences in the size will not matter when you are performing the act of classification in the vacuum. So whenever you are performing the classification process, you think that, okay, because of the difference in the weight of the particles, but because of the difference in the size of the particles, when I allow these particles to fall through this cylindrical barrel, because of their difference in weight, they will fall at a different speed. If that is your imagination, and do this experiment in a vacuum, then you will observe that all these particles, irrespective of their sizes and weight, they progress at the same velocity and fall at the same time. This is primarily because you have just one force acting on this particle, and that force is the gravitational force, and these particles are accelerated due to the gravitational force, and the acceleration due to gravity is the one that is causing this particles to move at a specific velocity, at an increasing velocity across this barrel. So there is only one force, whenever there is only one force that is acting on these particles. So you are considering a cylindrical barrel in a vacuum, say it can be of 10 meters height, and you are placing, or you are allowing the particles of different sizes to fall through it. Now there is, I don't know, if you have time you could look up online. There is a wonderful video wherein they would show the falling of in a vacuum, the falling of a feather, or rather a feather and a bowling ball. So bowling ball is of some kgs weight, and the feather is close to nothing, and they allow these feather and also this bowling ball to fall in a vacuum, and they to our amazement, or to our surprise, or physically it is surprising to see that both this bowling ball that is of some kg weight and this feather which of no weight, they fall, they propagate, or they fall at the same velocity, and they reach the ground at the same time. So that is exactly what would happen when we consider, when we have such a setup where, irrespective in a vacuum where there is only the gravitational force that is acting, so irrespective of the sizes of the particles, all the particles will travel at the same velocity and they reach the ground at the same time. So that means it is difficult for us to consider or build, or difficult for us to separate these particles based on their velocity with which they travel in a vacuum. So essentially it is difficult for us to do the classification in a vacuum, or to put it in another way, it is difficult for us to perform classification when only one accelerating force, or only one force is acting. So only one force is acting. So essentially in vacuum what we have is, we have just the gravitational force that is acting, and since that only gravitational force is acting, and it is impossible for us to distinguish the particles of different sizes, because all these particles, they travel at the same velocity and they reach the ground at the same velocity. Therefore when you have only one force that is acting, so in this case it is gravitational force. So in a vacuum, like, so here the vacuum is for a thought experiment, and we saw that when there is only one force, for example the gravitational force that is acting, it is not possible for us to introduce or to separate the particles using the classification process. So for that what we need is, we need a counteracting force. We need a counteracting force, so that this counteracting force, in addition to that of the downward pulling gravitational force, ensures that the particles travel at a velocity that is dependent on their sizes. So when you have only one force that is acting, the size of the particle is immaterial, all the particles will travel at the same velocity. However, whenever you however, in addition to this one force, you include a counteracting force that depends on the size of the particles, then it will be possible for us to ensure that the particles travel with a velocity that is dependent on their sizes. So initially when you have a single force acting, this you have an independent velocity, independent of its sizes. Now in addition to a counteracting force, it is possible for us to establish a velocity that is dependent on the size. Now we can think of this rather in a simple manner. Now we talked about an experiment wherein a bowling ball and a feather is allowed to pass through, or allowed to fall in a vacuum. Now when we perform the same experiment, we allow the bowling ball and the feather to fall in a normal environment. In a normal condition, we allow these two particles to fall. One is the bowling ball of some kg weight, the other is object is a feather that is quite weightless. We allow these two objects to fall in a normal environment, not in a vacuum but in a normal environment. Now in this case, it is possible for us to predict, or it is possible for us to say that, or reasonably assume that the bowling ball will reach the ground faster when compared to the feather, because in the natural instance, in the absence of a vacuum, in the presence of air and other factors, what essentially we have is, we have a counteracting force, we have a friction that prevents the feather from moving as fast as that of the bowling ball. So that is, what we have essentially done is, we have essentially changed the medium. Initially when we considered a vacuum, the bowling ball and the feather, despite their significant difference in weight, they traveled at the same velocity and they reached the ground at the same point. Now, we are essentially changing the medium. This experiment we are performing it not in a vacuum now, in a general environment, in our current environment, and performing the same experiment wherein we are allowing the bowling ball and the feather to fall. But now, because of the resistance that is offered by the environment, so in the environment, what the difference between the vacuum and the environment that we consider is, in our environment we have air. Because of the change in the medium, now instead of vacuum we have an air medium. In this medium, because of the change, because of the friction that is offered, because of the resistance that is offered by the air, the bowling ball is allowed to pass through. It is allowed to travel much faster than that of the feather, and the feather will rather float when compared to that of the bowling ball, and the time taken for the feather to reach the ground will be much slower. So therefore, now here, based on their velocity, based on the time taken by these particles to reach the ground, we will be able to separate the bowling ball from that of the feather. So therefore, what essentially we understand is, when we have a medium that offers a contracting force, then it is possible for us to differentiate the particles based on their size, based on their weight, because the velocity with which they travel in that medium will vary. So here, these particles, irrespective of their sizes, they travel at the same velocity because they are solely governed by acceleration due to gravity. However, if you change the medium from vacuum to a fluid medium, this fluid medium could be air or it could be anything. So if you change this medium from vacuum, if you replace the vacuum medium, then essentially you are introducing a contracting force, a resistance. It can also be, in most instances, it is friction. And this friction, the way this friction is imposed on the particles depends on their weight. Some particles, because of their sizes, because of their weight, it is able to overcome this friction. Some are not able to overcome, and now therefore there will be a disparity in the velocity with which they travel across this particular cylindrical barrel, and based on that, now the classification is possible. So what classification, when you consider the theory of classification, what classification theory requires is two counteracting forces. So one is an accelerating force that governs accelerating. Pardon me if my spelling is wrong. So you have an accelerating force, and you also have, in addition to that, you have a counteracting or a resisting force. You have a resisting force. So because of the combination of these two forces, you have a specific velocity that is achieved by the particles that depends on its size, and essentially it depends on its mass. So with increasing size, we can only assume that for a given particle the mass increases. So therefore, the velocity that the particle achieves, it depends on the size or it depends on its mass. So once there is a disparity in the velocity, be it depending on its size, depending on its mass, once the disparity in the velocity is achieved, then it is possible for us to classify these different particles traveling at different velocities based on the time taken by this particle to reach the end of the barrel. So that is the theory behind the process of classification. So for classification to occur, you need to have two contracting forces. One is the accelerating force, the other is the resisting force. So when you consider the falling of a heavy bowling ball and a weightless feather, here the resisting force is nothing but the friction that is offered by the fluid or the air that surrounds our environment. So with the presence of this friction, with the presence of the fluid, it is possible for us to offer a resisting force. So therefore, the process of classification is always conducted in the presence of a medium, and this medium is often a fluid. The fluid can be air or any liquid, but you cannot do the classification process in a vacuum. You need a specific medium for it, a specific medium that could offer a resistive force, and this resistive force is referred to as, in a more technical term, as a drag force. So you have a combination of accelerating force and a drag force that establishes or that is principal for the process of, that is vital for the process of classification. So even though it is the combination of the accelerating force and the drag force that brings about the disparity or the difference in the velocity with which these particles travel, now there is one inherent feature of the particle itself that allows for this distinction to occur. So in the absence of a resisting force, all the particles will travel in the same speed. So in the presence of a resisting force, there is a difference in the velocity assumed by each of these particles that is dependent on their sizes. Now again, when we consider size, what we assume that all the particles are made up of the same, or all the particle composition of all the particles. So all the particles have the same mass. So therefore, when you increase the size of the particles, so essentially you are increasing the mass. So what we essentially assume that when you increase the size, the mass of the particle correspondingly increases. This is only possible when the chemical composition or when the constitution of all these individual particles are the same. Now supposing if there is a significant difference in these particles in such a way that the mass of the smaller one particle of smaller size is equal to the mass of a larger particle, then in that case you will not be able to establish this difference. Let me repeat, it is possible to have a small ball of made up of iron that is of 1 kg, and we cannot have a similar small ball of sponge that is made up of the same weight. So if you have a small ball of iron that weighs 1 kg, in order to have the same amount or in order to have the same weight of sponge, we need to have a significant portion of it. The size of the 1 kg sponge would be quite huge. So therefore, it is not the matter of size, but it is the matter of density. So even though for a given particle, even though for a given mineral particle, the sizes will increase or the mass will increase with size, when you have a mixture of particles that comprises of gangue and mineral, the factor that dictates the factor that governs the velocity with which these particles will progress through the medium is nothing but its density. So that is the reason why we considered or compared the iron with that of sponge. So essentially, when you have the iron of weight 1 kg, it can be as small as a ball. However, the same amount or the same weight of sponge will be quite huge. So therefore, it is not the matter of the size, but it is the matter of weight. And if you look closely what we mean by weight, it is nothing but the density, because density again, if you consider its expression, is mass by volume. Now volume is dependent on the size. So therefore, when we say that particles of different weight, they travel or assume a different velocity while they are progressing in this iron barrel, or while they are progressing through the iron barrel while doing a classification process, what we essentially mean when we say that particles of different masses, they assume different velocity or they travel with a different velocity during the classification process, what we mean by that is the mass here is the product of its volume, the volume of or rather the density of the particle and its size. So this is what we mean when we say particles of different masses, they travel with a different velocity during the classification process. So classification process is principally, to have a quick overview of what we have seen so far, classification process, it depends on or it classifies the particle based on the velocity with which these individual particles travel. And it cannot be performed in a vacuum, because in a vacuum all these particles, irrespective of their weight and size, they travel at the same velocity. So therefore you need a specific medium for it. This specific medium can be as simple as air, or there can be other unique medium for it as well. Now what this medium does is, medium brings about a counteracting force to the accelerating force. Often the accelerating force is the gravitational force. To that accelerating force, this medium brings about a counteracting force, so that the influence of the mass of the particle is ensured. So when we say the mass of the particle, what we mean by that is, we mean the product of density and its size. So depending on the size and the density, the combination of the size and density, we are able to classify the particles during the classification process. We are able to separate the particles during the classification process. So essentially, it is not only dependent on size, but it is also dependent on density. So therefore, this classification process is more close to concentration than that of screening, because in screening we are not worried about the density. All we are worried about is just size. So irrespective of the density, we are not concerned about the density. Irrespective of the density, if a particular particle satisfies a given size condition, it can be screened during the screening process. It is allowed to pass through the aperture during the screening process. However, in case of classification, we are, in addition to considering the size, we are worried about we are concerned about the density of the particles as well. So supposing if we have the combination of two different particles in a given mixture, like we usually have, we have the combination of gangue and we have the pure mineral particles present in a mixture, then during classification, if there is a significant difference in the density between the mineral particle and the gangue particle, it is possible for us to classify through this classification process, and therefore the classification is more close to the concentration process than that of the screening or the comminution process. So that is the reason why the classification acts as some intermediate step, between the concentration and the comminution. So in classification, we consider the density, and if you have a gangue which has a significant difference in density when compared to the mineral, it is also possible for us to separate the gangue particle from that of the mineral particles through the classification process. So essentially, the classification, it separates the particles based on the velocity with which they travel, and this velocity, it depends on the mass of the particles, and when you consider the mass, it is rather the mass dependent on two factors, that is the density of the particles and the size of the particles. If the density is equal, it is just independent. If the density of all the particles are constant, it is just dependent on the size. If not, it includes both density and the size. Now, when we say there is this combination of an accelerating force plus a drag force that is acting during a classification process, because of this accelerating force and a drag force, there is a constant velocity that is achieved by the falling particles, and this velocity is referred to as the terminal velocity. So essentially what we have is, in the setup of the classification, you have two different forces, two contracting forces that are imposed on the given mixture of particles, and because of these counteracting forces, the particles that are falling through the medium, that are falling through a given fluid, they achieve a constant velocity. So greater your accelerating forces, greater will be your drag force, and this balance will help us achieve a constant velocity. This is what we refer to as the terminal velocity, and depending on the terminal velocity through which or in which the particle pass through the medium, we are able to classify our particles, and this is what the fundamental operation or the mode of classification, how it is achieved in the. So it is how the classification is achieved, and this is the principle behind the whole process of classification. So essentially, when we say we are during classification, all that we do is consider the velocity with which the particles travel. What we are essentially considering is, we are considering this terminal velocity, and this terminal velocity is achieved by the balance between the accelerating force and the drag force. And when you have a constant terminal velocity, when the terminal velocity is rather constant, then you will be able to appropriately separate a given set of particles from the other one. Now, let us, in order to understand the theory behind, in order to gain how these drag forces is imposed on the particles that are falling across a given medium, let us consider particles of that are propagating through two different velocities. So what we essentially want to know is how this drag force acts, how this resistive force acts when a particle falls through a given medium. So because this drag force is what plays a critical role in achieving the terminal velocity. So we want to know how this drag force acts in a way to bring about this terminal velocity, to bring about this constant velocity, because in the absence of the drag force, what you essentially would have is not a constant velocity but an increasing velocity. It is this drag force that brings about a constant velocity. Now let us see how this drag force brings about the constant velocity. Now when we see a particle in a given medium that is falling at, so to understand how this drag force acts, let us consider a particle that is falling through a given medium, and it is falling at rather a low constant velocity. So a particle is falling through a given medium and it is falling at a relatively low constant velocity. So let us assume a similar barrel, and in that you have, instead of having air, you have a specific medium. So instead of placing this barrel in a vacuum, we have this barrel rather filled with a specific medium, a specific fluid, and you allow a particle to fall through, and this particle assumes a velocity, a terminal velocity that is relatively low. Now when this particle is falling through at a relatively low terminal velocity, again the terminal velocity is dependent on the mass, and when you consider the mass, that is covered by the density of the particle and its size. So the terminal velocity is governed by it, and now we have a particle that is falling at a very low terminal velocity, falling at a very low rate. Now when the particle is falling at a very low rate, what happens is, once you have this particle hitting the medium, you have a specific medium surrounding the particle. You have a specific medium surrounding this particle. So supposing we will assume that this medium is a liquid, and from air, from our natural environment, you are feeding in this particle. You feed in this particular particle into this medium. Now once you feed in, there is a layer of this medium that surrounds this particle. Once the particle enters into the medium, there is a layer that surrounds this particle. Since the particle is progressing at a low velocity, this neighborhood of this medium will not change as the particle progresses. So essentially you have a particle that is falling at a very low speed and in a medium. Now once you introduce this small particle, or this particle that will be traveling at a very low speed, there is a cover, or there is a surrounding that is being produced by this medium. So this medium forms a cover, this medium forms a surrounding, and then around this particle. So this surrounding around this particle, the blanket formed around this particular particle, it continues as the particle progresses down the barrel. So essentially when the blanket that is formed in the initial stages, once you drop this particle into the medium, a blanket is formed, and this blanket continues till the particle reaches the end of the barrel. So when you have a particle that is progressing through the barrel at a very low velocity, what happens is, the first event that happens is the formation of a surrounding that blankets your particles, a formation of a blanket. So this blanket, it comprises of the medium. So this is the first event that occurs when you place or feed in these particles that will progress at a low speed. So when you feed in a particle that will progress at a very low speed, first event is the formation of the blanket. Now this blanket, it remains undisturbed. It remains undisturbed all through the journey of this particle. So this blanket is sustained all through the journey of this particle. Now whatever friction, the drag force that is acted upon by the particle, so whatever drag force that is imposed on the particle, so since this particle is traveling in a specific medium, whatever drag force is imposed, it is not imposed on the particle itself, but rather it is imposed on this blanket here. So essentially, when you introduce a particle onto a medium, there is a blanket formed around it by the medium, and this blanket is sustained all through the propagation of the particle, and because this blanket is sustained, whatever drag force is imposed is not imposed directly on the particle, but it is imposed on this blanket. And this, so essentially what we have is the drag force is not imposed on the particle directly, but on the blanket. So you have three distinct events when the particle is progressing at a very low speed. One is formation of a blanket, and the drag force. Now this blanket is not disturbed; it is sustained as the particle progresses across the barrel, and whatever drag force is acted upon, whatever is imposed, it is imposed not on the particle but on the blanket. So essentially the resistance now is not between the particle and the medium, but the resistance is between one layer of the medium and the other layer of the medium. So therefore this is referred to as the viscous resistance. So essentially what we have is, we have the resistance that is imposed within the medium itself. You have a specific portion of the medium that surrounds the particle, and this specific portion of the medium, it is interacting, or it is rather experiences a resistance from the other portion of the medium, and this is observed when the particle is progressing at a very low speed, and this form of resistance is referred to as the viscous resistance. So viscous resistance is observed when the particle is progressing down the barrel at a very low velocity, and it comprises of three distinct events. One, formation of a stable blanket. So a blanket is formed, and this blanket is sustained all through the progress of the particle. The reason is it is sustained is because the particle is progressing slowly, and now because of the sustained blanket that surrounds this particle, the resistive force, the drag force, is not directly being imposed on the particle, but the layer of this blanket. So the blanket is what experiences this resistance. So whatever resistance we have is between the blanketing medium and the surrounding medium. You have a blanketing medium and the surrounding medium, and the resistance is between these two layers, and therefore it is referred to as the viscous resistance. Now, on the other hand, when we consider a particle that is traveling with relatively high terminal velocity, then what would happen is this formation of blanket still remains the same. Once the particle is dropped onto the medium, a blanket again will be formed. However, because of the increased terminal velocity, the blanket is no longer stable. So in case of high velocity, or in case of a particle that is propagating at a high velocity, what you essentially have is, you would have particles or the blanket being formed, but these blankets will be unstable in nature. So we will have an unstable surrounding to that of the particles. So you have an unstable surrounding, you will have an unstable blanket, and therefore essentially these blankets keep on changing. These blankets, as the particle progresses across the medium, the blanket gets worn off, and they get removed, and new blankets needs to be formed. So in this case, the resistance is not between the stable layer of the blanket and the remaining medium, but here the resistance is between the particle itself and the medium, and the blankets keep on changing. So therefore, the resistance that the particle experiences when it progresses with a very high velocity, we refer to it as the turbulent resistance. So depending on the velocity with which the particle is progressing across the medium, it is possible for us to have two different drag forces or two different forms of resistance. So both these experience a drag force, and then the particle is falling at a very high speed. The resistance is experienced directly by the particle. The resistance is between the medium and the particle itself. So that we refer to as the turbulent resistance. So we don't have any buffering medium between the particle and the ones that are offering the resistance. Now in case of the particle that is progressing through a very low velocity, you have a formation of a stable blanket. You have a formation of a stable surrounding. Now in this case, the drag force to the particle is imposed by through this blanket, through the surrounding medium. So therefore, in that case, the resistance is between the surrounding medium and the other medium. So the resistance now in the case of the particles progressing at a low velocity is between the blanket and the surrounding medium, and therefore we refer to that as the viscous resistance. So with this theory on how the drag force is imposed on the particle, how the resistance is imposed on the particle, how it depends on the velocity with which the particle progress, with which and how it depends on the ultimately the size of the particle. So this depends on this difference in the resistance depends on the velocity with which the particle progresses. So again, the velocity with which the particle progresses for a given medium depends on its mass. So with this understanding on how the resistance is imposed on the particle, we will wind this lecture up, and in the subsequent lecture we will build on this current understanding. Goodbye.